This is Amar Gandhi, and this is my teach one on the comparison of means, question 4. So the first step is to download the files. So go to this link, data.cms.gov, and all that, and then use the data sets from between 2015 to 2019 annual files. So it'll look like this, different annual files, and then once you open one of them, like this 2019 annual file, once you open it, within each annual file, you download the latest zip file, the one whose date is closest to December. So this one is the closest one to December. This is October, so we download this one for 2019. Then we unzip all the 5 folders uh, that was downloaded onto our computer, and then we copy the 2019 uh, HCAPS hospital file that's inside the unzipped hos underscore revise underscore flat files underscore archive underscore 10 underscore 2019 folder, and place it in the parent folder, which is the folder containing all the hos revised zipped and unzipped folders. After it's pasted in the parent folder, you have to rename it by adding underscore and then the year. So in this case, it would be 2019 at the end of the file name. So for example, the HCAPS hospital file inside the HOS revised flat files archive 10 2019 folder should be copied and put into the parent folder and then renamed to HCAPS hospital underscore 2019 so we can differentiate which one was from which year. So the next slide shows that this is how we copy it. Copy this HCAPS hospital file, and we're inside this 2015 or 2019 HOS revised flat files archive 10 2015 or 2019, sorry, and we are copying this file, and then we paste it in the parent file, which is just the question 4. So just one step back in the directory, and and then you add the underscore 2019, and then so eventually once you do it for all the years, it'll look like this in your where you saved it. Then we open a new Jupyter notebook and import these 4 packages: import pandas, numpy, math, and matplotlib. Then we read the 5 CSV files we'll be using by typing in data underscore 2014 equals pd dot read underscore CSV, and then the file path where you put R, and then apostrophe, and then the file path where you saved it, um, and then the engine, and then comma engine equals Python. And do it for all 5 of the data files. So for an example, I can show you. So to do that, you click on the HCAPS Hospital 2015 file, CSV file, where it's saved on your computer, and then you go to your Windows. If you're on Windows, you can go to your File Explorer and then click Copy Path, and that will copy the full complete file path, including the file name, and then paste it in Jupyter Notebook on the previous slide, and add that comma engine equals open quotation, Python, close quotation, and then close parentheses at the end of each line. So, and that's how we're repeating it for all the remaining 5 years, like 2016, 17, 18, and 19 CSV files. Then we preview the first row of the data frame for 2014 by typing in data underscore 2014.head, and then parentheses, and then put 1 inside to look at the first row. That's what the first row looks like. Then we preview the first 3 rows by typing the same command except putting in a 3 instead of 1 to see the first 3 rows. And these are the first 3 rows. Then we display and bold column names for each data frame. So the input would be, you would write print /033 bracket, open bracket 1M, and then close quotations plus 2018 data types plus the same thing except instead of 1M it's 0M. So you do that for each, and then you print that data underscore 2018 dot columns, and do that for each of the years, 2017, 16, 15, and 14. And what that does is it bolds the whatever's in the middle, which was the 2018 or 17, 16, 15, 14 data types string. Then so right here you can see everything is bolded, the headers. Then inside each is the different columns. So this is the output, and the main difference is that you have to watch that 2014, 15, 16, and 17 all have provider ID and hospital name, but 2018 it changed to facility ID and facility name. That's the only difference there. And you select only a few columns to be present in separated data frames you create. So you create separate data frames with a limited number of selected columns for each time period. So we only want to look at these columns, not all of them. So that's why we just selected these: provider ID, hospital name, city, etc. And we're focusing on the HCAPS measure ID. And what to look out for is the 2018 data filtered, the data frame. It says start date and end date, whereas the other ones say measure start date and measure end date. So you just have to be careful there. Then we check the resulting data frame for 2018 by previewing its first 5 rows, and that's what it looks like. I mean, if you just type in .head, then you don't need, then it previews automatically the first 5. You don't need to put a number in. Now we look at the data types for all 5 years while bolding the headings. So again, we're going to be bolding these headings: 2014 data types, 2015, 16, 17, 18. And then HCAP's linear mean value is an object data type that needs to be converted to a float data type. You can see here it's highlighted. The HCAP's linear mean value is object, and we need to convert it to float. So now we check for non-numeric data in the HCAP's linear mean value column, and a series of error messages, the main one being the value error. So we'll be getting this value error, which shows that it couldn't convert the not available string to a float data type. So when we try to do HCAP's linear mean value dot as type and change it to float, we get a bunch of error messages, and it ends with this is the last error message: value error, could not convert string to float, not available. So that means it couldn't convert. So um, we replace the not available entries with 0 and convert the linear mean value column to float data. So this is how we work around. Um, so here we're converting it to 0, np.nan, and then comma 0, comma regex true. We did it everywhere. And we're forcing it to do it despite the error, so we're coercing it. That's why we wrote that there. Then we view the updated column, so we bold 2014 HCAP mean value float type for each of the years. And then you can see instead of it showing an error, it shows 0 for all the things that have been highlighted. It says float, data type is float, and the value is 0 for all 5 of the years. Now we're viewing the first 5 rows of data, 2018 filtered data frame, and that's what it looks like. Then we're applying conditions to the data frame. The input, um, you would have to write all of this provider ID for the hospitals we're looking at are here, and then the hospital name is here, Sibley, right, is right here, and then the other competitor DC hospitals are around it here. So we want to look at all these hospitals by their names here, and the city is Washington or Washington DC. Then we're writing dot is in city, so that city will be Washington. So all of them are looking at is in Washington DC. Then the output is here. It shows their linear scores. Um, for 3 hospitals from 2015 to 2018, the same 3 hospitals, but then for 2014 this included 7 hospitals, which are the 7 we're interested in. Now we find the shape of each data frame. We're doing print data 2014 filtered to dot shape, and we get it's 7 rows by 7 columns, each one. We calculate the average satisfaction at Sibley Hospital across the 5 time periods. Um, so from 2014, looking at the linear mean value for the HCAPs, and that's the satisfaction, and we're looking at the mean for it. And then 2015, we're doing the same thing, same with 2016, 17, and 18. And we're printing those averages here. These are the averages 78, 84, 86, 85, and 87 for 2018. Now we're calculating the average satisfaction at competitor DC hospitals from 2014 to 2018. So do the same thing, except for hospital name, we put not equals to Sibley Memorial Hospital. So that means it's all the other hospitals in DC except Sibley. So that's what we do here. And again, facility name is here and hospital name is here. So it changes for 2018 compared to the other years. And we're doing the mean, and then we print the average for all the other competitor DC hospitals. We get 79.833 for 2014, 81.33 for 2015, 81 for 2016, 82 for 2017, and 81 for 2018. This is the combined average. Now we create a data frame that contains both Sibley and competitor DC hospitals data from all 5 years to determine the grand average. So we're creating a data frame that includes all the HCAP's linear mean values for all the years. And we add headers of all satisfaction for 2014, 15, 16, 17, and 18. Then we concatenate or combine together all of them in one table, and we preview the table. This is what it looks like. Only 2017 is shown. We calculate the grand average and standard deviation. So grand average for DC and Sibley hospitals is 81, and the standard deviation for DC and Sibley hospitals for all the data across the 5 years is 5.9. We create a data frame containing satisfaction data for all DC competitor hospitals from all 5 years. Again, only 2017 is showing. Now we check for normal distribution. We're looking at normal distribution for 2014, 15, 16, 17, and 18, the linear mean values. And we produce this histogram which shows that it is normally distributed. Next, we determine average and standard deviation for all competitor DC hospitals. So we first take the average per time period, um, and then we print them here. Then we find the count of hospitals in each year. We're doing int data frame 1 status 2014 dot count. Doing that for each year, printing it. Then we get 6 for all the years. And the z-stat is 1.96. Then the standard deviation per time period is standard deviation for 2014 is standard deviation of all the years divided by the square root of n for 2014. And that was calculated as 6. So all these n underscore 2014, 15, 16, 17, 18, they're all 6. So that's how we come up with the standard deviation for all the competitor DC hospitals, which are all the same value, which is 2.41 approximately. Then we create a data frame supporting the calculation of UCL and LCL. So the z-stat value is again 1.96. And the data frame 3 we're including the years, average satisfaction in Sibley Hospital, the average in 2014, the standard deviation in 2014, the average of all, and the z-stat. We're doing that for each of the years. As shown here, 2014, 78, 79, etc. And then we're adding column names to the data frame. So we're adding year, Sibley Memorial, average satisfaction for competitor DC hospitals, standard deviation per time period, average satisfaction for all the hospitals, and z-stat. So that's shown in this table here. Then we're calculating UCL and LCL, which is for UCL, it's the satisfaction for all that data frame plus data frame for z-stat times the data frame standard deviation per time period. And for LCL, for competitor DC hospitals, it's data frame for average satisfaction for all minus the data frame for the z-stat or times the df4 for standard deviation per time. The only difference between UCL and LCL is it's the for UCL it's the average satisfaction for all plus the z-stat score, and then the average satisfaction for all minus the z-stat score is for LCL. Then we do the last step, which is plot the X bar control chart, and we're adding. So this is what it looks like after you add all the labels. So we can see that Sibley Hospital performing better than most of the competitor DC hospitals. And so we answered the original question, which is, are satisfaction levels in Sibley better than its competitors in DC? And we determined that patients are more satisfied with Sibley Memorial Hospital than with the other competitor DC hospitals. And control limits for the other competitor DC hospitals are based on a 95% confidence interval around an average satisfaction rating in competitor DC hospital. Thank you.